Hello class, and welcome to the quiz 3 pre-quiz review. I know you're all working hard towards preparing for quiz 3, which is this week 12. And so as usual, I figured I'd help you with your preparation by creating this pre-quiz review where I try to highlight the more important theory that we've learned in each of the chapters, and also walk you through some problems that I think are important to actually have understood the main points of the chapter. But also these problems are more along the lines of what I will likely put into the quiz for you to answer. So there's a benefit for you both ways. You get a good refresher on the theory that you have studied, and also some problems. You don't have to do all of the problems. It would be nice if you can refresh all the problems we have done, but at least pay attention to these problems that I will cover in the pre-quiz review, for your benefit. Okay, so I'll move on. I'm on slide 1. I'll move to slide 2. On slide 2 on my PPT, I have listed the 4 chapters that will be covered in the quiz. So the quiz will be about these 4 chapters, and these were the chapters that we completed after our last quiz. That means the last quiz was in week 8, right? After that we covered these 4 chapters: diodes, BJT, MOSFETs, and CMOS digital circuits. CMOS digital circuits only part of it that we covered in week 11. I know right now in week 12 you're going through some new material. I'm not going to put that into the quiz, so just the first part. Okay. Alright, so I will try and do this review in 2 recordings. So the first recording I will do chapters 4 and 6, the diodes and BJTs, and then the next recording I'll do chapters 5 and 13, MOSFETs and CMOS digital circuits. Okay. Alright, let's move on to slide 3, and I know everything here is pretty small in size, but I went to full screen mode, so hopefully this helps a little. Let's see. So what is it that we studied in this chapter called diodes? So we started off with some definition of the ideal diode, and then we introduced the junction diode, or the PN junction diode. Now the ideal diode never exists, but it has some good properties that makes it easier to understand the logic. For example, the ideal diode, as soon as the forward bias is just anything over 0, right? So as long as you have a very even slight positive voltage on the anode and negative on the cathode, that's forward bias, just slightly above 0, it goes into full conduction. Similarly, on the reverse side, anything slightly less than 0 will get you the reverse bias, right? And we did some more problems and all that in it. You can take a look if you have the time. But the ideal diode was a good idea, a good concept. More important is the junction diode, which revolves or is based on the PN junction that we studied in the earlier chapter on semiconductors, right? We were introduced to the idea of doping the P side, the N side, and if you put it together you have a junction, and the junction is a natural diode. So for the junction though, the properties are slightly different from the ideal diode. So for example, a proper forward bias only happens after about 0.5 volts on the positive side. That means your anode has to be about 0.5 volts, not just 0, 0 or slightly greater than 0, but it has to be 0.5 and greater, and then you can see that the current starts to conduct in the forward direction, and it rises pretty steeply as an exponential, but this is the forward. Similarly, on the reverse direction, we know that very little current flows even as you keep increasing the reverse bias. Uh, the reverse bias current I equals Is into something is pretty steady, but if the voltage in the reverse direction goes beyond a certain value called the breakdown voltage, then or the knee voltage as they call it, Zk, then it starts to operate in a funny fashion in the breakdown region with a constant voltage drop but high current, right? So forward direction is kind of mirrored in the reverse direction. And this region is called the breakdown region, and we saw that there was some benefit to operating a diode in this region also. So we studied all this, and then an important relationship is obviously the diode current, right? I equals Is, which is a fixed value. It depends on all these p-n junction parameters, the area, the Ni, intrinsic doping, intrinsic carrier density, and then these other factors, lengths and doping constants and so on. So all these give us Is, and once you have Is, you can write I in either direction as Is is E V by Vt. Vt is a constant, it's the thermal voltage, right? And that's the formula. Now if you have a negative for the voltage V, that means it's in the reverse direction, and if you have a positive, that means it's in the positive direction. So this can be approximated for large values as I equals Is E V by Vt. Also, the opposite of this gives you V equals Vt natural log I by Is. So if you know the ratio of I and Is for two different points and you want to know the voltage, then you can use this formula. If you only know one voltage, you can find the current in this way. Okay, and then there's your expanded view of the breakdown region in the reverse direction. So all this was kind of the introduction to the diode. Then we studied some modeling. That means instead of having to draw this every time, can we simplify by having some voltages and some resistances instead of the whole diode. And so we saw an ideal voltage model, we saw a constant voltage drop, right? So we assume that this is a straight line, this abrupt exponential rise is a straight line, and then you can use this constant voltage drop model for the diode. The exponential model is like what it really is. And then we also worked on understanding the small signal model. In fact, we were introduced to the idea of a small signal for the first time. And a small signal model generally consists of two pieces. One is what's called the DC or biasing model, or the biasing voltages, and the other is actually the signal voltages, right? So how to separate the two is something that we were introduced to. As long as the signal is truly small, right? Once the signal becomes very large, then you are not in the linear portion of the operating characteristic anymore, and so you cannot use the small signal model. But if the signal value is very small compared to the biasing values, then you can use it. Okay, use the small signal approach. So in the small signal model, the diode is just replaced by a small resistor called Rd, right? And then once you draw a circuit like this with an Rd, I also introduced you to the idea of the load line, and how the fact that you, with a given load for the resistor, or the given load resistor, in this case I think it's R1, you can actually draw a load line, and then you put that on top of the natural characteristic of the device. In this case, it's a diode. We use the same approach for BJTs and FETs also, MOSFETs. But in this case, we have a diode characteristic and a load line, and where they intersect is called the operating point. And so the small signal model, or the small signal approach to finding the current in the diode, is you add the sum of the bias current, which is just a DC value, plus a small signal current, which is V by R. And for R, we use this small signal model RD that we just defined, which is actually defined as VT by ID, and it's called the diode small signal resistance or incremental resistance. So then the small signal circuit becomes like this, and you can solve some problems using this. One more time, on the reverse side, we were introduced to the idea of the Zener diode. A Zener diode is a special diode that is designed just to work in the reverse direction under breakdown conditions mostly. And the applied voltage is always the opposite, right? Because we are working in the reverse direction, so the anode is negative and the cathode is positive, and we are working on this side or this side of the diode characteristic. One of the big reasons why we work like this, I mean, any diode can be used like this, but a Zener diode is specially designed to work like this, and its big benefit or its big application even today is in voltage regulation. So what that means is, even if the current changes through the diode circuit very highly, all the way from there to there, you see that the voltage really doesn't change much, right? So the voltage is almost constant. And so voltage regulation means maintaining a constant voltage, or as constant as possible. There'll be always slight change, but mostly constant, even though the current changes very significantly. The current might be 3 or 4 times change, but the voltage changes hardly 1 or 2%. And that property is called regulation, and diodes in the reverse direction are used for that function. So we finished this and this. Then we have the important section on rectifier circuits, right? We spent a lot of time understanding various rectifiers, and we derived some formulas. In fact, we had a lab on rectifiers. So I hope rectifiers are something you become quite comfortable with. So I show here a half wave rectifier to the left, where we only have one diode and a capacitor and a load resistor, right? Now you can have a rectifier without a capacitor, in which case the ripple will be very high. So to reduce the ripple and to introduce kind of a filter, a simple filter, right? I mean, you can have very complicated filters, RLC circuits and all that, but we only studied some simplest possible filters. And so the capacitor is a filter, and we derived some expressions for the output voltage, the ripple and all that for this filter. Then we also looked at full wave filters or rectifiers. This is a half wave, right? If you apply an AC, only the positive half is used, the negative half, nothing happens, it's just discarded, or the voltage output stays zero. But if you use a full wave rectifier, you have 2 diodes with a center tap transformer, or you can have 4 diodes in a bridge circuit without a center tap transformer, right? So we studied both of these, and then we also put a filter capacitor on the full wave rectifier, and then we studied that. So let's see. Yeah. I got rid of the margin at the bottom. So what you see here is some expressions for the output DC voltage here in a bridge circuit with a filter capacitor, right? The RL is the load resistor, C1 is the capacitor, and the full expression for the output voltage in this circuit is V output DC equals Vp, which is the value here, or the value here, Vp, the peak voltage of the AC sine. Actually here there's the Vp here. So the input to this bridge is an AC sine wave, right? And that, or cos wave, and that is shown as Vp cos 2 pi ft, right? Here. So take that Vp, V peak, minus 2 times the drop in the diodes. Each diode is about 0.7 volts, so you can drop that, minus the ripple by 2. What's the ripple? The ripple has its own formula, depends on the capacitance, obviously, because the larger the capacitance, the less the ripple, we know that. So there's two formulas I've given you, one with where we ignore this diode voltage. Now this is the more correct value, right? But if you have very low ripple, if the C is very large and the ripple is like 1 or 2% of the output voltage, then you can ignore the minus 2 VD. But otherwise I advise you always to put this formula for the ripple, because you get a more precise answer, right? Similarly, the output voltage, you can ignore the ripple and just take this approximation, but do that only if you know that the ripple is very, very small. Otherwise, it's better to use the full voltage expressions, okay? So we studied these circuits, and then lastly we studied the limiter circuit, right? A limiter is used when we want to cut off the very high peaks of the input voltage. So in this case it's a sine wave, and you can chop off the top. You can do the same on the bottom direction, but this only shows you how to do in one direction. So we did some circuits, you guys also did a lab, so hopefully you remember, you know, all this material. Okay, so this is what we studied as far as the theory goes. I mean, we studied a lot more, we spent plenty of time on it, but those were the main highlights of you know, all the material we looked at. Okay, so I got a couple of problems that I want to look at on diodes. I just picked some of the more important ones where we cover a lot of material to help you understand diodes better. And also from an exam perspective, I think these are important. Okay, so here's one example from the textbook. So this is solved in your textbook, and it's example 4.5. And let's look at it in some detail. Okay, so consider the figure shown in case A, right? This is in figure A, sorry. R is given to be 10K. The power supply V plus is 10 volts. Now, in addition to this 10 volts, there is a 60 hertz sinusoid of 1 volt amplitude. So there's actually a ripple riding on this DC, right? So that's what's been given, and the value of the ripple is 1 volt peak amplitude. The question then says calculate both the DC voltage of the diode, that means the voltage here, and the amplitude of the sine wave volt signal appearing across it. Actually, the value of the sine wave signal is given, right? It's 1 volt 60 hertz peak. So that's given. All we have to do is to find the DC voltage. Assume the diode to have a 0.7 volt drop at 1 milliamp current. So all this data is given, and we have to find this the DC voltage of across the diode, right? Okay, so let's see. I mean, I've given you the results, I think, already, but we can see how he solves it. But anyway, the first step is to find the diode current with a 10 volts drop. So with the 10 volts drop, we have been given that there is 0.7 volts at 1 milliamp, but we have also been given this. So using this formula, we come up with 0.93, which is pretty close to the 1. So we can assume that the voltage drop is 0.7. Now, how to find RD in this model, right? RD according to the formula is Vt by Id. So that's 25 millivolts divided by 0.93 milliamps. That's why I didn't show you the millis, or he doesn't show it. And it comes out to be 26.9. So this value is known. So now you can, obviously calculate the value using the voltage divider formula, the diode voltage, which comes out to be 2.68 millivolts. So it's solved. Let me open up the chapter. Yeah, I think this is it, to 4.5. So I don't want to repeat the whole thing again. I mean, same thing. He gives you why he uses these formulas, etc., and how to find the peak value on the diode side, given that on the input side you have this 1 volt peak, right? So on the output diode side you get a 2.68. This is the signal value, right, not the DC value. Okay, all right, so that was one problem that I thought you guys should all revise in preparing for the exam. Next problem I've shown you is actually from the back of the chapter that we did. I know there were 3 problems in a row, 4.78, 4.79 and 4.80. I think I did 4.78 and 4.80 myself as part of class problems, and the one in the middle, 4.79, I asked you to do it for homework. So this problem I think we should review. So let's see what the problem asks us to do. So it's required to use a peak rectifier to design a DC power supply that provides an average DC output voltage of 12 volts. So the output voltage is given to be 12, and a ripple of plus or minus 1 volt is allowed. So there's a ripple and then there's the steady DC voltage. This rectifier feeds a load of 200 ohms. So the load is 200 ohm resistor. Now the rectifier is connected to the AC line voltage. This is the American line voltage in the house, which is 120 volts RMS, 60 hertz, through a transformer. So there is a transformer that first steps it down from 120 to some value, to some lower AC value, and then the rectifier bridge is connected, not a bridge, but in this case I think it's a half wave circuit. So that is connected to the secondary of the step down transformer. The diodes have 0.7 volt drop when conducting. So for a half wave circuit, here's all the things that we have to find. We have to find 5 things: A, B, C, D, E. A, find the RMS voltage that must appear across the transformer secondary, right? That's question 1. Then there's a filter circuit, because you have a ripple. It's not a large ripple, so you obviously have a capacitor. So find that required value. Then find the maximum reverse voltage that will appear across the diodes. Well, it's one diode because it's a half wave circuit. And specify the PIV rating, the peak inverse voltage rating, which is different from the maximum reverse, right? I think you probably know that. Calculate the average current through the diode during conduction and calculate the peak diode current. So all 5 items. Then we also have the same problem. Everything is pretty much the same, but now do it with a full wave bridge rectifier, right? And the reason we go with a full wave is because the half wave can give you a value of capacitor that can be very large. But if you have a full wave rectifier, then you can have a more smaller size capacitor. Of course, now you're spending money on many diodes, but sometimes it's easier to buy more diodes than it is to buy a big capacitor. And big capacitors need a lot of space. They have other problems. So that's why the bridge rectifier, full wave rectifiers are preferred. Anyway, so we have this problem. So let's quickly look to see how we solved it. Okay, so I'm going to open my diodes notes. and go straight to that problem. It's on my PDF called Chapter 4 Diodes Class Problems Part B. I think for diodes we had a Part A and a Part B, so this is Part B. And here on page 8 on the top I show you how I solve the problem. So we are given plus or minus 1 volt ripple maximum value. That means the ripple is 2 volts peak to peak, right? And we should also always specify ripple as to peak value. So the output voltage is given as 12 volts plus or minus 1 volt. That's how you write it. R equals 200 ohms, the load resistance. So I immediately is this DC by R, right? So that's 0.06. Now the first thing you do is to find that Vp, which is the transformer secondary voltage, right? That's the value here, secondary side. Sometimes it's shown as Vs, but Vp is what we use in our formulas. So I should have made that a Vp, I'm sorry. So using transformer secondary voltage, V output is Vp minus Vd minus Vr by 2. Now these formulas are different for different rectifiers. So make sure if there's a problem in the exam, you should pick the right formulas. They are different. Some of them are different, not all, but some of them can be different for different. The ripple may be different, the output may be different. So given V output, we find Vp, and this is, I'm sorry, I had a DC originally, but it's actually an AC value. Vp is an AC value on the secondary of the transformer. So if you know the peak value, and this is a peak, so how do you get the RMS? You have to do by root 2. So remember that fact. And don't mix up your DC and AC. Okay. Now to find the capacitance value, we are given the ripple value, so we know this is the formula. So you just move C to the other side and you come up with this value. So this is a pretty large capacitor, right? 542. Maximum reverse voltage is this formula. So that's 25.7. PIV is 1.5 times 25.7, so that's 38.5. Then there's formulas for DI average and DI max. Okay. So learn to use these formulas and become familiar with them. So we also looked at problem 480, which was the same exact problem, except now we have a bridge, right? So again, VR, is 12 plus or minus 1 volt, R is 200, and IL is 0.06, which we calculated in the previous case. Nothing changes there, okay? To find Vp, now the formula is slightly different. I think there's a 2 here compared to the previous one, but you find Vp, which is an AC value, as peak value is 14.4, RMS is divided by root 2, and you get that. You need the RMS to specify this, right? Yeah. Now ripple is Vp minus this formula, and so you can find the capacitance using this formula, and now it's much less in this case compared to the half wave. Maximum in reverse voltage has this formula, and so PIV equals 20.5, and then we calculate ID average and ID max. Okay, so C is lower, PIV is lower by 50% because we went with a full wave rectifier. Okay. So that's all I had for diodes and that chapter on diode. All right, let's move ahead. As always, we are running short on time, but we also will do BJTs in this recording, and then I'll move to the next one. So let me see if I can expand this to full size so we can read what I wrote. All right, so we were introduced in the beginning of the BJT chapter to the NPN transistor and the PNP transistor. And immediately we were told certain things, right? That there's an active mode, there's a saturation mode, and there's a cutoff mode. So in active mode, the base emitter junction has to be forward biased. Actually, both for active and saturation, the base emitter junction has to be forward biased. That means the BE has to be at least 0.7 volts because this is a diode, right? And if you have 0.7, you know, yep, it's properly forward biased. Cutoff is when that falls below that 0.7, then the transistor is cut off. On this side, the other junction, which is the collector base junction or collector emitter, you can, for active, you generally talk in terms of VCE has to be greater than 0.3 volts, right? That ensures that the transistor is in active mode. Generally, you can also say if the VCE is greater than VBE, equal or greater, then it's in saturation. You can be in it's in active mode. You can be less than VBE for a little while until you get to 0.3. That's called soft saturation by some writers. But even that is considered active. So as long as your VCE is greater than 0.3, you're happy, you're in active mode. If it falls less than 0.3 is when the transistor becomes saturated. Okay. Similarly, for the PNP, all you have to do is, instead of calling these voltages VBE or VCE, you just flip them around and you say VEB and VEC. Once you follow that convention, then the values stay the same. You don't have to worry about, negative values and all that. So that makes it easier to understand, I hope. Okay. So remember, the base emitter junction has to be forward biased. The collector base junction has to be reverse biased for active operation for both transistors. Okay. Then we looked at some ways to draw the circuits to make it easier. So the NPN is generally drawn like this. The emitter is always grounded. Even though we draw in the beginning like this to understand, the most commonly used forms of circuits are like this, right? With the emitter downwards, not like the emitter here shown upwards. Similarly, for PNP, the emitter is shown up, the collector is shown down. The reason we do that is because we always believe that the higher points, physically they are higher, are at higher voltages and current flows downwards, right? We use that throughout our circuits courses, circuits chapters. So to follow that same rule, this is the best way to draw circuits, okay? So because the collector is at the highest positive voltage always, it shows high, it's at the topmost point, the base is somewhat lower, and the emitter is at ground, and it's flipped around for the PNP. Okay, so with that we were introduced to a whole bunch of equations and some new parameters. So first of all, I emitter, right, equals I collector plus I base, because we know all the current from here goes into here and it's divided into the base current and the collector current. So the I emitter, the emitter current is almost equal to what is the collector current. A part of it goes into the base. So base current is always very low compared to the emitter or the collector, and the collector current is almost as much as I emitter. And we were introduced to these two terms, beta and alpha. Beta is generally high, 50 to like 200 or so, and alpha is 1 by 1 plus beta, or beta by 1 plus beta, and it's generally slightly less than 1, right, 0.99 or something. So understand why those are important, the alphas and the betas, and also the fact that all these currents can be written, they're related to each other through the alpha and the beta. Okay, so that also, I didn't bring that out anywhere here, but make sure you get a good handle on how betas and alpha help connect IE and IC, etc. So for example, I collector is alpha times I emitter, right? So it's about 0.99, 0.98, etc. Times I emitter, and so on. This relationship is very important. I collector equals IS, which is that diode saturation current, right, times EVBE by VT. So this proves to you that the collector current depends on the base emitter voltage. So in this configuration, this collector current depends on this base emitter voltage and almost nothing else. So that's why we'll come to the models in a bit, but this is an important relationship. Okay, then we looked at a variety of other um, uh, graphs, graphs and relationships, right? So here are some graphs which connect the VCE, the collector emitter voltage, to the collector current, right? Um, Then we also have another graph called the VTC that connects the output, which is the collector emitter voltage, to the input voltage, which is the base emitter voltage. So this VTC is important. These graphs are important to understand the operation of the transformer, of the transistor, and also the Q point, the biasing point, right? So pay some attention to all these. Let me also look at these two circuits. These have to do with understanding how to specify a certain DC operating point or DC bias point, right? If you want a certain value of uh, um, the collector current or a certain value of the collector to emitter voltage VCE, then you need to be able to design the resistor values, right? So there's many different biasing circuits. We are not going to study too many of the biasing details in this course. I keep telling you, you'll study more of this in the next course, EE380, where you'll have plenty of time as to why we need strong biasing circuits. Why can't you just use a simple resistor? How does it help the designer, etc., etc. So all that we'll do later. You guys will do later. But for now, I just wanted, in this course, you just needed to know that there is something called a bias circuit, and that generally means you need to know if there is a, you of course need to know the resistance in the collector circuit, but you also need to sometimes know if there is a resistor in the base circuit. Sometimes there's only one resistor, sometimes there's two resistors, sometimes this base voltage VBB is different from VCC, sometimes VB or the base is also connected to the same voltage as the VCC. So many options exist. Some of them we studied in some detail. For example, this is a voltage divider circuit in the base. So part of this can be applied to the base to become the base emitter voltage, right? So these circuits we studied. Please take a minute to revise all that and become familiar, so that you are not surprised if you see an exam question on biasing, etc. These two relationships are important. The top one, in fact, is quite important. Both are. This is just KVL written around this circuit or around this circuit, right? But this top one also becomes the voltage amplifier equation, right? So for the first time, I introduced you to the idea of an amplifier. So what does the amplifier do? If there is a small signal in the input, which is in this case the base circuit, then you should see a magnified version, a higher with a gain more than 1 on the output side, which is the collector to emitter voltage, right? So but since our relationship is only in terms of output current and input voltage, then we say that instead of worrying about output current, I see if you put it through a resistor, then you get an output voltage. And how is that related? Through case KVL. This is the equation, and then you can also modify it to show VCE, the output voltage, as a function of VBE, the input voltage. And in fact, we have a parameter called GM, transconductance, that also helps you connect the output current to the voltage. Okay. So these two equations are important, and then of course the VTC tells you how the output, which is the dependent variable, varies based on the input, right? So as the input goes high, the output stays flat for a while and then drops. The active mode, the saturation mode, and the cutoff mode, right? Three modes of operation. And this edge of saturation is at 0.3 volts on the VCE. So I hope these ideas are you're familiar with by now, because you studied PJTs, then you studied FETs. So hopefully these don't seem strange to you anymore, I hope. The last section was something called small signal analysis. Sometimes I can get rid of this, sometimes I can't seem to get rid of this. Okay, there you go. Let's move it here. Press again. So small signal analysis is when you have on the input side, which in this circuit is on the base side, you have a bias voltage, it's the big VBE, and then you have a signal voltage, which is a small VBE, right? You know how this circuit is connected, and then we use really the principle of superposition, and this principle of superposition applies as long as we are in the linear operating range, right? And this VTC, we assume that this central portion is linear. You don't want to be here or there, but as long as you are in the middle portion, that means you pick a Q somewhere in the middle, and your transistor only operates slightly around that, then we assume it's linear operation. And for linear operation, you have a simple superposition that gives you the output total voltage and total current, right? Total voltage and total current, meaning the output V base to emitter, this is the input, right? On the input side, you can say V base to emitter is V base to emitter, capital, big one, that means the DC, plus the signal VBE, right? That's on the input side. On the output side, similarly, you have a current which is in the this circuit, the collector circuit. So that current is the sum of the bias current, big IC, plus the signal current, small IC. And we have equations for each one of these, which are simple algebra, not nonlinear. We don't use exponential and all that. As long as the signals are small and the transistor is in the linear region and it's not in saturation, right? With these conditions, we can see how a small input on the base circuit gives you this big output on the collector side, right? So revise this material, look at my notes until you become comfortable with those ideas. Also, I'll tell you these equations are important because you can definitely expect some questions around, like based around this. So here is a bunch of relationships and new factors, parameters that were introduced. So the transconductance connects the output current directly to Vt. So it's almost like it's only dependent on the, because Vt is a constant, so it's pretty much only dependent on the collector current, which we know depends on the input voltage also, right? The VBE, the biasing voltage. But here's an expression for the transconductance. Here are two more resistors which are used in the small signal model, right? R pi is this resistance. This is the resistance looking into the base emitter circuit, that's called R pi, and then the RE is looking into the also into the input circuit, but looking from the emitter side. So R pi is looking from the base side and RE is looking from the emitter side. So these are the relationships. They connect alpha GM to R pi and RE, and so you should become familiar with what these are and how they are used here, okay, in the small signal model. The small signal model, I know there's a lot of material in the textbook, but let me just talk about this one quickly. This is the hybrid pi model. There's also a T model, but basically what the hybrid pi model says is that the transistor can be modeled as a voltage controlled current source, right? This is a dependent source and it's a current source, as you can see from the arrow, but the value of that current depends on the input voltage. So this voltage VBE is what gives you the value of this, and this VBE uh, is depending obviously on this input, but because there's a base resistor, they are not exactly the same. If this didn't exist, then the two are the same, but because there's a biasing resistor, so VBE then gives you the value of what the output current will be in the collector circuit, and to get that you have to first multiply it by GM. So this is the small signal model, and if there's a resistor, a load resistor RC or other resistors, they all get connected here, and if there's other stuff here, they are connected here, and you can solve some problems using simple KVL and voltage divider methods because you have drawn the small signal model. Okay, so that's the benefit of having the small signal models to help us solve problems. One last thing I'll point out, two things. One, the voltage gain, right? That's a very important part of why we study transistor circuits. The voltage gain is defined as many things. Actually, there's a lot of formulas. One, you can get the voltage gain. I mean, the first important formula is the change in output voltage by change in input voltage is the voltage gain, right? That is pretty easy to follow. But it also can be derived directly from such things as the ICRC and the VT. It also is connected to GM. So become familiar with all these formulas for the voltage gain, because you never know what you will be given in a problem and which approach, which formula to use. So if you become familiar with all of them, it'll help you solve problems. Similarly, the currents, all the three currents, the IC signal current, the IB base current, and the IE emitter current, all are connected to these parameters, the small signal parameters, in this way. So IC is GM times the input voltage change, IB is the base emitter voltage signal divided by the input resistance R pi. Similarly, IE is the same VBE, but this time divided by RE, which is the emitter small signal resistance. Okay. All right, so that's the theory. I hope that helped. You should of course spend more time looking at my main notes. Here is all I've tried to do is try to give you a quick summary, but the main content is not only in my PowerPoints, but if you have time you should also study the textbook material itself, right? All right, so let's move on. I have about 10 minutes I think to do some problems. So I have 2 or 3 problems that I want to look at. First problem is a simple problem called collector current, and here we are given a circuit and we are given some values for VCC 3 volts, VBE is given to be this battery 750, and there's no other resistance, so this whole thing can be considered VBE, the biasing voltage. And then we are told to consider this VCE to be Vout, right? This is VCE. So also IS is given, right? That's a constant. It's 5 times 10 power minus 16. He says find VCE basically. And if beta is also given, find the values of IE and IB. So I thought this was a good formula that connects, or good example that connects many things in one. And as a hint, I have already given you the important equation, which is KVL for this collector circuit. Okay. All right. So let's see if I can find my notes. Yeah, this is BJT. Yep, we are still in BJT, and this is on page 1 of my BJT class problem solutions PDF file. Here I've drawn the circuit again, and I have listed IS and beta. So find V out. Using first step, to find V out, we will use that KVL equation, right? This equation to find VCE. But to use this equation, you have to at least know IC. Everything else is given, so all you need is IC, right? And to find IC, you use this equation. VBE is given, VT is generally 25 or 26 millivolts. Use that and you come up with a value of 1.69 milliamps. Once you have that, you use it in this KVL equation, 3 minus IC RL. Instead of RC, I'm using RL here. It's the same thing, RL. And so you come up with 1.31 volts. Now you can actually answer one more question right away here. VCE is 1.31 volts, and we know VBE is 750 millivolts, right? So can you tell that this is an active mode? Yeah, because anytime VCE is greater than 0.3 volts, you can say that the transistor is in active mode. So remember that fact. If VCE as calculated, which is also V out here, if it's greater than plus 0.3 volts, the transistor is in active mode. Okay. Another way to say it is, if VCE is greater than or at least equal to VBE, then automatically you don't have to calculate, you can just look at it and say it's in active mode. Then the part B says beta is given, so we know alpha, right? And so find IB and IE. Because we have IC is beta IB and IC is alpha IE, we know these relationships. So using that, you can find I beta and IE through these relationships. Okay. Note that IC is always approximately equal to IE because it's only slightly different based on the alpha. Okay. All right. So that was the one problem I wanted to look at. Let's see what more we have. We have a couple more problems to look at. There's a small signal gain example 6.13. So I'll go to it in a minute. Here is a simple amplifier circuit, and this is example 613. IS is given, collector resistance RC is given, VCC is given. Determine the value of the bias voltage VBE required to operate the transistor at a certain VCE, right? So that's given. So if you know VCE, he wants us to find IC and VBE. Then find gain. Then if there is a small, then the next question is what VBE positive increment. That means what signal can we add to the basic VBE so that the transistor goes to the edge of saturation. That means it's driven to where any more and then you'll go into saturation. So what is that limit? That limit is VCE is 0.3 volts, as I just mentioned. So what value can you add to VBE in the positive direction so that VCE becomes the limit, which is 0.3, the saturation limit. And then on the negative direction, if you put VBE in the negative direction, then the transistor goes in the other way, which is towards cutoff. So what is that value? Okay. So look at example 613 where these equations are used. V2 minus V1 is Vt log I2 by I1, and then delta VBE is this. So let me see if I have time to go there. We can shut this. Okay, I think I have to go forward significantly. Almost to. Yeah, I think here is, yeah, it's on page 400, 613. Okay, so the same problem is here. So here's what he does. First, IC equals VCC minus, using that KVL, you come up with IC. Once you have IC, you can use it in this equation for IS, because IS is yeah, IC equals IS times this, right? So we know IC, we know IS, we can find VBE, and that's 690 millivolts. Then gain, in this case he uses this formula. This is also one of the important formulas. That means the voltage drop across the resistor in the collector circuit, right? If you put that on the numerator and divide by Vt, you get this equation. I think it's somewhere in my notes here. Yeah, see this formula in the middle, AV equals minus ICRC by Vt. This numerator ICRC is nothing but this, right, ICRC. To get that, you can take the difference between that and divide by the current, and you will get, or divide by the resistance, and you will get the current. But the product of these two is this voltage. So this minus this gives you the output voltage. Divide by that by Vt, and you should get the gain as one of the formulas to use. Then if you know that the input signal is 5 millivolts, how do you get the corresponding output signal? You multiply by the gain. So that's one thing he does. Then for VCE to be in saturation, right, that's 0.3 volts. What is the value of IC? It has to be this. What is the corresponding value of VBE to achieve that, the delta? So if you have a small 12 millivolts signal that you put on top of the regular biasing voltage VBE, if you add 12 millivolts to this 690 millivolts, then you are pushing it to saturation. That is the answer. Similarly, you are pushing it to cut off on the other side by adding a VBE of minus 105 millivolts. Okay, so this is a pretty large value, but this, even a small value, pushes it to saturation. Okay, so that's the logic here. I think it's an interesting problem. Spend some time and become familiar with it. It will help you in the exam. Okay, last problem is a transistor amplifier again. This is example 614 from the textbook. Here the question is simple. Find the voltage gain VO by VI, and VO is shown as to be the DC value plus the signal value, and you see the way the circuit is drawn here. You have a biasing value battery VBB, you have a small signal, and then the two are in series and they go through a biasing resistor into this, right? So we did this. I hope you remember. This is 614, and let's see, 614 in the textbook is right here. So we wish to analyze the transistor amplifier to get the output voltage gain VO by VI. So he walks you through these 4 steps, A, B, C, D. He draws the model here and uses it to answer some questions. Here's the 5-step process. The first step is to find the Q point, then various other steps. So each one of these leads you to the answer. So he determines the small signal models in step 2, RE, GM, RPi. Then he creates the model, which is this. Then he answers the question. VBE is using the voltage divider formula, and then as a last step he finds VO or the gain actually as VO by VI using this formula, right? So there's many formulas to find AV. I'm sure you can think of other ways to find it. You can even use just the GM times you know IC, right? That's another formula uh, to find AV. So there's different formulas, but the approach he takes is to go through step by step. He knows the input value, the input voltage signal, he finds the output voltage signal, and then he divides the two. Okay, so spend some time on this problem because it covers a lot of important ideas, and I think that will definitely help you be better prepared for the test. Okay, so I'll stop this recording here and do the next recording to cover the remaining two chapters.